Okay, can you hear me and see me okay?
Yes, that looks good. Yeah.
Okay, perfect. So welcome to one of the labs that we have here at Royal Holloway. So this is the, one Accelerator Lab that's shared it with the, you'll see the dark matter lab in a second that Adriana is just setting up on the other side. But we have a number of different experimental areas that we use for research, of course. So developing key pieces of equipment that are then shipped out to somewhere like CERN and installed and tested at the, for example, at the Large Hadron Collider. So there are various pieces of exciting things to show you. The one that I've picked for now, as time is a bit limited, is actually related to this EO-BPM project. So electro-optic beam position monitor. What we have essentially here is a device that's a test stand to put a pickup that has this electro-optic crystal inside it, and it will go and be tested by the vector network analyzer that's behind me. So just to remind you a bit about the idea. So what we're trying to do is measure the crabbing, the bunch rotation of the protons as they pass through each other. So we want to be able to measure both basically the transverse displacement of the bunch compared to its propagation direction as a function along that bunch itself. Now the bunch is incredibly fast. It goes past in only 1 nanosecond. Is the 4 sigma width of the whole bunch. So we need something super fast that can monitor, you know, the kind of 50 picosecond time scale, the displacement. So this is a very ultra fast diagnostic. So we need to use rapid optics and the electro-optic effect in order to measure it. So what we essentially do is we send in laser light with a certain polarization state that goes through the crystal. And as the bunch passes by, that polarization state is changed. It's perhaps rotated according to the strength of the electromagnetic field that's detected at the crystal that's emanating from the bunch. And that's converted into an intensity variation of the light that's then recorded by a detector. I'll perhaps bring this a bit closer so maybe you can kind of see what I'm seeing. So we have, for example, here, let me see, what can you see? Have I got that lined up roughly right? Let me point with something. So we have, this is just a simple laser going through some polarization optics. We then have a mirror, it bounces through off the mirror into the pickup. This tube here is similar to, it's mimicking the LHC beam pipe through which the particles would travel. In this case, we're putting an electrical signal through that beam pipe and then recording what comes out the other end. And at the same time, we're recording light that comes out of the pickup and it goes into a fiber and then into a detection device. So here we're just calibrating this device for a moment, but soon the idea is that we will then take this over to CERN, install it in the accelerator at CERN and really measure the beam for the first time. And once it's all set up and running, then it will be deployed to measure regularly the crabbing of the LHC bunches. In fact, in 2018, this crabbing technique was tried in the SBS for the first time using these special, basically metallic boxes called cavities, where you pump in an electromagnetic wave. And what that does is it makes the box resonate in a certain way. And that gives the bunch a kind of a kick. So as the bunch goes through the box, it will rotate it, it will kick it in the transverse direction and give it this interesting crab. And that was detected. The first crabbing of a proton bunch was detected a couple of years ago at CERN. So now we know the concept kind of works, and we're now developing the diagnostics to really be able to measure this very, very precisely. So this project, it would involve a little bit of optics, getting some hands on with the experiments here at Rutherford, first at Royal Holloway, and then going over to CERN and setting up the experiment at at CERN and taking the data there, so being stationed at CERN for some time with the PhD. The first year would again involve the lectures at the John Adams Institute and the training that we have to offer there. Okay. How much more time do I have, Ronit? Do you want me to go somewhere else, like downstairs, or perhaps I could show you?
You can, because at the same time it will sort of show us a bit of the department.
So I'll give you a general little tour. So at the moment we have, this is the dark matter lab. In fact, Adriana's over there, so I won't spoil her excitement. You'll see that shortly. Perhaps what I'll do is, I mean, there's various other bits and pieces. So in the dark rooms over there, we have the pyroelectric accelerator setup that I was mentioning. We have various devices. Let me take you on a quick tour of the department and hope my Wi-Fi doesn't kick out at the wrong time. So we have, there's a computer room, so I'm going past the HIT lab. I hope you may have to take over, Veronique, if the Wi-Fi fails at any point.
Yeah, so far it's fine, yeah.
So
except now we lost Stephen, but I think he will reconnect once he gets downstairs. It's just see, let's give him a few seconds to see if it reconnects when he gets to the next location.
Actually say laser on.
There you go. Okay, we just got you back.
Oh, okay. Sorry, it does say laser on. So let me just see if someone's not there. Hang on. And open the door. Oh no. Have to open 2 doors at once. It's quite difficult whilst
holding a
laptop.
I hope we're not violating some safety protocol here, Stephen.
Probably are. Probably are. Ah, there we go. I can do it. Here we go. Ah. Oh, no, it's not working.
It's okay. Maybe we can go to Adriana and Harrison, and then
okay, fair enough. I think
come back at the end if to sort of help you sort of juggle laptops and keys and doors
that be fair enough.
and pin pads. Excellent. Okay, thanks so much, Stephen. And if I can ask,
here comes. I think Alessio is inside the room. He's about to open the door. Ah. Hi, Alessio. I'm sorry.
Yeah, sorry.
Should we carry on for a little bit?
Okay, yeah. If you want to do 2 minutes or so.
We're just doing a tour of the department live to loads of people. Would you mind us just popping in?
Yeah, sure. Just come in here, and then I'll switch off the laser from the other side.
Thanks.
Sorry, I was working in there.
No, that's fine. Is the laser on or off?
Yeah, at the moment it's on. But,
okay. Okay, well, yeah, okay.
Hi.
So hi. So that you can. This is kind of an unprepared part of the tour, so it's a little bit haphazard. But that's research, right? It wouldn't be the same if it wasn't somehow like this. So this is our portal into the laser room. So we have lots of equipment currently piled up. The laser, we have an internal safety interlock, which is normally hard to get through, especially if you're holding a laptop. But this is obviously to protect personnel. And yeah, if we just pop into the laser room. So we're also working on, this is where we're working on one of the laser wires for the front end test stand. Okay, thanks, Alessio. So we'll come in here. So if we wander in, you can see hopefully a range of different equipment. So this is a rather powerful laser. I don't know. Alessio, do you want to say anything very briefly, like 1 minute about a laser?
This is a mod-locked laser, so it produces pulses at with 10 picosecond time, and high repetition rate of about between 1 megahertz and 65 megahertz. And this is the laser that we are basically, developing to do our experiments at FETS.
Okay.
So where we collide these laser pulses with the H- to produce sort of signal related to the longitudinal or transversal mode of the accelerator.
Okay, that's awesome. Yeah. And what do we have here? We have a nice breadboard. I don't know if you can see, but it's maybe a bit more light. Yeah. You can see the shape has been cut out. So this is where the beam pipe will sit. This will actually be a vertical breadboard. And you can see the two laser beams will come in this direction. And this basically allows us to measure the two transverse planes of the beam that's traveling, in this case, in the vertical direction. So you can scan the laser this way, or you can scan the laser that way in order to measure the width, if you like, of the particle beam. Yeah, I think that's probably enough.
I think that's great. That's really good. So thank you so much for that. Thanks, Alessio. And
no problem.
And at the same time, we got a bit of a change of location, which was great. So thank you, Stephen.
Thanks, Alessio. Thank you.
Good. So if I can ask Adriana to maybe turn on your camera.
Yes. Okay.
Great.
Hello,
I can see
everyone.
you. Yes. Very good.
Let me see. Let me try. Okay. This is probably going to fail. I'm trying to switch to the nice camera, and now it's frozen. But it's all right because I will continue talking whilst the camera gets. There we go. It's working. Yeah. All right. So I'm a second year PhD student in the dark matter department. And my project is one of the two projects that I will show today where it is not necessarily looking for dark matter, but is using tools and methods that are used to look for dark matter, but to use it in other experiments. So my project focuses on environmental monitoring and specifically on detecting concentrations of lead in water. So lead pollution is a big problem. I mean, you can just look at the situation in Flint in Michigan in the US. And we found that it's quite expensive to do lead assay in water. So developing countries really struggle to do this, to understand what are the levels of contamination of lead in their water. So we are using CMOS devices to attempt to detect this concentration of lead in water and at the limit that is provided by the World Health Organization, which is 10 parts per billion. So to begin this project, we started using a scientific CMOS and to develop a calorimetry code analysis tools that would allow us to understand, how low can we go in terms of concentration of lead in water. So that is the first thing I'm going to show you. So let me see. So in order to do that, you should be seeing the dark box now. And this is in the same lab where Stephen was just a moment ago. So in order to start our experiment, the first phase of it was to use this CMOS here and to take data with it. So we've spent, I would say, probably 6 months using different radioactive sources, which you would place here, and then just acquiring data with it to understand what was the lowest activity we could detect with the CMOS, which turns out it was around 100 parts per billion, so not as low as the World Health Organization limit, but we're working on it. We continue to do some research on it, and now the next step of it is to find how other much cheaper CMOS devices can do lead detection in water. So that's what I'm working on at the moment. So the next project that I want to show you, well, it's not much to show, it's just this tiny silicon photomodified tube, which you can see here, which is also inside the dark box. And this SIPM comes from the dark side experiment, which is also one of the experiments that our department is involved in. And this experiment is searching for dark matter using liquid argon. And these sensors are around 1 centimeter squared. So I don't know if you can see it. I don't want to damage it. And they're quite sensitive to single photons, as traditional PMTs would be. But unlike traditional PMTs, they have very low levels of dark count rate when they operated at very low temperatures. And they're very good. They have very good signal to noise ratio and very good higher photon detection efficiency. So here we're testing the timing performances So we will have a pulse light source, which has not been yet installed. So this has just begun, I would say, a month ago. And you're just trying to check the response to particle interactions in the silicon itself. So the idea is to see if in this experiment you can search for dark matter not only using liquid argon, but also in the sensor itself. So if we now move on, I will try, I'm on a trolley, so I'll try not to shake this too much. So there, over there is the accelerator part where Stephen was just a minute ago. And it's a very messy lab. There are lots of people working it. So finally, this is the final experiment I want to show you here. And this is an experiment that is, again, using methods used in dark matter and used in medicine. So again, it uses liquid argon, which has a very high light yield of 51 photons per kilo electron volt. And liquid argon is relatively cheap compared to other scintillation mediums that would be used in nuclear medicine. So the aim here is to build a liquid argon cell, which I don't know if you can see, it would be there. And then they wanted, the student that is working on this wants to test this detection efficiency, again using silicon multipliers, and then to slowly scale this in order to have a complete positron emission tomography scanner, so a PET scanner. And then they're using germ simulations alongside this experiment to just determine its geometry and its properties, and then eventually they want to test a full PET scanner. That is the aim. So yeah, that's just three. Oh dear. Okay, still in one piece. So that's just three experiments that we're working on here in Dark Matter Lab. So I suppose I will stop now and take it to
Thank you so much, Adriana.
No
so very useful, and we were able to see and hear everything as if we were there. So there you go. Now, if I can ask Harrison, maybe to turn on your camera, and then similarly to Adriana, I think just turning on your camera might be fine. There we go.
Oh, we have got the room. Let me just.
Excellent.
Okay.
That's great.
Hi. So I'm Harrison. I'm a PhD student here at Royal Holloway, working on the high pressure time projection chamber experiment. This is a particle detector for neutrino physics that you can see behind me. I'm here in one of our clean rooms, hence the hat. So currently the detector's role is to be a testbed or prototype for the near detector of the June experiment. This is a deep underground neutrino experiment at Fermilab and Sanford Underground Research Facility over in Chicago and South Dakota. They're studying neutrino oscillations, and they want to use some of the old TPC readout chambers from ALICE, one of the LHC experiments, as part of their detectors. They want to operate their detector in a high pressure gas. So currently here at Royal Holloway, we're testing if the readout chambers from ALICE will work in high pressure gas. So behind me, we have a pressure vessel. This can operate at pressures up to 5 bar. We use argon gas, since this is what June will be using in their detector. And if I can turn my camera around without breaking anything, on the table here, we have one of the ALICE readout chambers. So this is just on the table at the moment. We are cleaning it to put it in later in the week. I apologize about the angle. This is the best I could do with the webcam. But this is a multi-wire proportional chamber. So we'll be testing that in the pressure vessel behind me. Like I say, right now we're just cleaning it. We're putting that in tomorrow. We'll be operating that here at Royal Holloway with radioactive sources, developing all the electronics and software we need, and then at some point we should be taking it to Fermilab in Chicago to test it in a beam. So I can show you some of our gas systems here, and I can't show you a full TPC at the moment. I just have some other parts over on the other side of the room. Some of these field caterings. I can talk a bit more about the TPC. I think we're running out of time. I could stop there.
You have 2 more minutes easily, so you can go ahead with 2 more minutes if you want to.
Yeah, sure. So our detector is a time projection chamber, or TPC. So the way that this kind of detector works is that when charged particles enter into the volume. For us, that's high pressure gas. These charged particles ionize the argon, they produce electrons, and then we have an electric field in which the ionization electrons drift towards the readout chamber, which I just showed before. And here we have a much stronger electric field. The ionization electrons are accelerated, producing more ionization electrons from the gas volume, which in turn do the same. So we get what's called avalanche charge multiplication, where one electron producing the TPC can produce several tens of thousands of electrons, which we can detect and measure and extrapolate backwards to learn about the original particle which entered the volume. I can't show you again the full TPC, but we do have just those field caterings that I showed. If I turn that around again, the whole thing is sort of a cylinder. These are the field caterings. These maintain the drift field, which the ionization electrons drift under. So you can hopefully at least see that the whole thing is cylindrical. At one end of that would have this readout chamber. Again, we have this on the table at the moment.
That's great.
I think that's all for me, unless.
Yeah, I think that sounds really good. So thanks again for this. I'm here. So let me stop the